Hello, my name is Asuji Alwihari from the AWS Messaging and Automation team, and today I'm joined by Sandeep Dumad of S&P Global Ratings to talk about how to migrate mission-critical applications that use messaging over to AWS. So before we begin, let me just talk quickly through what we're going to cover today. I will start first with a high-level introduction of enterprise messaging. Then we'll talk about a service, Amazon MQ, that was launched at reInvent in 2017, and a new advanced feature we recently launched in December last year called Network of Brokers. I'm going to talk a little bit about network of broker topologies and their applications, and then I'm going to hand off to Sandeep, who will introduce S&P Global, what their needs were, and discuss how and why they adopted Amazon MQ. And after that, we will pause for a summary and a little Q&A. So diving in, let's start with a quick introduction of messaging. Messaging allows different software systems written in different languages on different platforms, potentially running in different locations to communicate and exchange information. Just like compute and storage, messaging is a fundamental building block of enterprise applications. And it's used in a vast number of use cases, from financial services to media and entertainment. In this case, we're showing an example in retail where a message-oriented middleware or message broker is used to connect the ordering front end to the back end, to the inventory system, to their CRM system. There are many examples of message-oriented middleware in the enterprises today: IBM MQ, TIBCO EMS, Oracle WebLogic, and open source solutions such as RabbitMQ and Apache ActiveMQ. As you probably know, AWS has several messaging services. The ones you've probably heard of are Amazon SQS and SNS. These are built for developing applications that are born in the cloud. They are extremely scalable and extremely reliable, but they achieve this scale and reliability because they have a relatively simple set of features. They are based on a custom API. They don't support advanced messaging constructs, say, such as request reply patterns or exactly once delivery or support for unlimited file sizes. But they are very scalable. What we found is if you are migrating applications that were built on industry standards and were written with lots of features, it's actually quite hard to migrate over to SQS and SNS. So a couple of years ago, we started to talk to enterprises about why they were not using SQS and SNS when they onboarded to AWS. And what they told us is they typically have tens or even hundreds of applications that use these traditional constructs and traditional APIs, and migrating was quite hard. So that's why we introduced Amazon MQ. Amazon MQ is a managed message broker for Apache ActiveMQ that makes it easy to set up and operate message brokers in the cloud. So you can migrate your applications without having to rewrite a lot of code. We run a message broker in a selected instance type, and we charge by the instance hour. For those who are familiar with, say, RDS, you can think of Amazon MQ as RDS for message brokers. Amazon MQ gives you a broad range of features and capabilities. The first is that it is a fully managed implementation of Apache ActiveMQ. It is not a fork. It is ActiveMQ 5.15.x, whatever the most recent version is. And because of that, it is able to provide a broad API compatibility with protocols such as JMS, AMQP, MQTT, Stomp, WebSockets, to name a few. With Amazon MQ, it's extremely simple to create a message broker. You go to the console, you select create a broker, you pick instance size, and in about 10 minutes, your broker is up and ready to go. And we provide broker scalability. So we provide vertical scalability, starting with instances, for example, the T2 micro instance, which actually has a free tier. You can create a broker with the T2 micro instance, do your experimentation and prototyping. And then as you scale up and go into production, you can pick brokers in the M5 series from M5 large all the way up to M5 4 XL. With the release of Network of Brokers, we also support horizontal scalability, where you can now scale your requirements by adding brokers to the network. Amazon MQ also provides high availability brokers. So we provide an active and standby broker in 2 separate AZs. These brokers are actually connected um, with a shared storage system. So they provide extremely high durability where all persisted messages are stored in at least 3 AZs. So messages are never lost when you use Amazon MQ. All messages are encrypted using service managed keys at rest and in transit. They're always secure. Your endpoints are created in your VPC, so your applications inside the VPC can communicate with Amazon MQ easily. If you need third parties or external parties to connect to your message broker, you can also create external endpoints. So again, added security features. Finally, Amazon MQ is tightly integrated with CloudWatch, so you can monitor your message brokers the same way you do the rest of your applications. We support monitoring instance metrics such as memory utilization, heap size, etc., or broker and message metrics as well, so you can see how many messages are in your queues and react as you need. So that's a high-level introduction to Amazon MQ. Last year in December, we introduced a service called Network of Brokers. Network of Brokers is a relatively advanced feature of ActiveMQ that connects multiple active brokers, both single instance and active standby, in various different topologies with what are known as network connectors. With Network of Brokers, you get increased aggregate throughput, you get higher broker availability, and you get zero downtime basically when you have broker failure. So if you can imagine in a network, you have multiple active brokers always going. If a broker fails, you can always immediately connect to another one. And with Network of Brokers, you can also configure your network to scale both your consumers and your producers. If you have large amounts of consumers and producers, there are topologies that allow you to scale and still maintain your optimal performance. So let's talk a little bit more about the basics of Network of Brokers. Network of Brokers is defined in each broker's configuration file by defining a network connector that interconnects the brokers. Network connectors are directed, so they can be duplex or non-duplex based on how you want messages to flow, depending on if you want the connector to be used both to produce and to consume messages. One thing is, by default, only active consumers connect to brokers and inform the network what queues and topics they want to subscribe to. So a broker does not know where to send a message unless there is a consumer present in the default form. Consumer subscriptions, when a consumer does connect, their subscription automatically propagates back through the network, telling brokers where messages must be forwarded. In order for a consumer to connect to multiple brokers, what they have to do is they have to use a failover string and a failover using the ActiveMQ failover protocol, which you define a string with all the URIs of the destinations that you want to connect to. So if you have multiple brokers, you add them to that string. The broker randomly selects where to connect, and if there's a failure, it reconnects to a different one, or not the broker, but the client. There's also something called a conduit subscription setting, which specifies if a connector between two brokers treats multiple consumers at the same destination as one consumer. What this means is, by default, conduit subscription consolidates subscriptions to the same queue or topic to prevent message duplication. This can limit traffic on the network and eliminate message duplication to those topics. However, it also impacts load balancing. And so if you're using queues and you want to distribute your messages evenly between consumers, you should turn this conduit subscription setting off. There are many parameters for Network of Brokers. We're going to talk about a few key ones. You can read about them all in the ActiveMQ documentation. Simple Google will get you to all of them, but let's talk about a few key ones here. First, of course, there is the name for the bridge, which can be anything you want, but make it descriptive so you can figure out where your bridges are connecting. You also need to define the same username, a username that has permissions in the broker, but has to be commonly defined across your network. You also define if the connection can be used to both send and receive messages using the duplex parameter that we just talked about. You must also use the URI parameter to define the endpoint that you want to connect your broker to. Then there is the conduit subscription setting that we introduced in the previous slide, where you define if the connector treats multiple consumers in the same destination as one. There are two TTL, or time to live, configurations. The first one is consumer time to live. This defines basically how many the number of brokers that subscription can pass through. So this should be set to 1 in the case of a mesh network, so that your subscriptions don't pass iteratively through the network. So the other one is a message TTL. This is the number of brokers a message can pass through, and this number must be larger than the maximum number of hops in the network in order to ensure that messages go through your network. There are two ways in which messages propagate through a network of brokers, and let's take a quick look at this. First, let's look at the default behavior, which is known as dynamic propagation. Here we're looking at a network of brokers with 4 brokers interconnected using 3 duplex or non-duplex connectors, here shown in orange. In this topology, messages propagate from the left to right and produces push messages at the left, and they propagate to consumers on the right. So let's consider a producer that sends a message to Q1 at broker 1. There are no consumers in this network, and the broker 1 knows nothing about the consumer, so the messages start to accumulate at broker 1. Now a consumer connects to broker 3 and subscribes to messages at Q1. What happens is that subscription passes through the network, traveling through every hop and informing every broker that they need a subscription to Q1. So now broker 1 knows that the message is required at broker 2, and it passes it on to broker 2. Broker 2 knows it needs it to broker 3, and that passes it on there, and then the message is delivered to the consumer. The other mechanism for propagating messages is known as static propagation. Here we have a similar network, but we have used the statically included destination sub-element to define that Q1 is a destination at broker 2 and broker 3. So if you look at the configuration on the right that shows an example, it shows the link to broker 2, which is the configuration for broker 1 showing a connection to broker 2. It gives you the URI where that broker is and the network TTL, but it has this statically included destinations element, which defines that Q1 is actually found on that connector. So here, if we look at an example here, the producer sends a message to Q1 at broker 1. There are no consumers, but the broker goes ahead and forwards that message to broker 3 because it has that already defined in Q1. So now when a consumer connects, the message is already there, and they can the broker forwards that message to consumer 1. So in this static propagation scenario, you can actually forward the messages before the consumers are available to do so. So there are many configurations, as I said, for network of brokers. There's different topologies, different things to set up. Amazon MQ makes it easier for you to set these up with the concept of blueprints. In the Amazon MQ console, when you select create a broker, you're given the choice of creating a single broker, active standby pair, or several network of brokers configurations. When you select create a blueprint here, it's created using CloudFormation. And then once that's done, you can actually go back and edit that CloudFormation template to modify, say, your broker topology, or even go edit each configuration file to modify the specific settings you need. So we create these simple topologies for you, but then we give you the ability to modify and add more settings there as well if you need to. For those of you who are not completely familiar with Amazon MQ, when you create a high availability broker, Amazon MQ creates an active and standby broker pair in 2 separate availability zones. These 2 brokers provide high availability for your messaging, And they also provide durability by storing all persistent messages across multiple AZs, so none are lost during a failover. If you choose to create a mesh network of active network brokers, of active standby brokers, you will get a mesh of interconnected pairs of these types of brokers. And each pair is connected using a special URI prefix called the master slave URI, which informs the network of brokers to connect only to one master at each of the brokers. So it automatically connects to the right place using that master slave URI. If the master is not available and it's switched over, it connects to the slave broker as well. So in this scenario, when a client connects to multiple brokers in this mesh using the failover string, like you can see here, it's connected to broker 1 and broker 2. They experience not only higher availability than just connecting to one active standby pair, so they have higher broker availability, but they also have high message durability and availability at each node. So if one message, if a broker should fail at any time. Let's take a little look at different topologies and kind of what that gives you in the market in as you set these things up. So the first one here is known as a full mesh, where all the brokers are connected to each other with duplex connectors. We are showing a 3-node full mesh here. Here, all messages are available at all brokers, and all clients can connect to multiple brokers to provide higher availability. So any broker can get to any message. And this is a relatively common topology for providing high availability. Sandeep will talk about it as well. And we make this available as a blueprint for you in the Amazon MQ console. Another topology to consider here is known as hub and spoke. Here, each connector is duplex and the clients connect at the edges. In this architecture, this is an architecture where everything can be set up in the hub with no configurations required in the spoke. So typically the hub, because of this, the hub has many network connections, and this has to be the most robust and performant broker. This is where you really have to focus your maintenance. And because all clients are connected at the spokes, the number of hops between any two brokers is always the same. So it is predictable. The one major downside here is, of course, there is a single point of failure. So if you lose that broker 1, no other brokers can connect to each other. The third one we look at here is something called Concentrator topology. If you have a large number of clients who may overwhelm a single broker, so imagine connecting to lots of devices or many users coming through different connections, you can consider deploying this concentrated topology. This is useful, as I said, when you have a large number of producers going to a small number of consumers, or a small number of producers going to a large number of consumers, which would be in the opposite direction. In this example, we have a large number of producers going to a small number of consumers or services. The concentrated topology is based on having multiple layers. Here, the producers connect to more brokers, so you can have a large number of producers connecting to a larger group of brokers, 3 in this case, at the top layer. These brokers then connect to the lower layer where there are fewer brokers, and these consumers connect to the lower layer. So what happens here is you can connect all those producers without overwhelming any single broker, but all the messages are available to the consumers lower down in the lower layer. In this model, you can scale up and scale down by adding brokers. You can also actually scale down by removing brokers, although you have to be careful in that scenario because you have to ensure that those brokers are trained and there are no messages in those brokers. So let's the last topology I'm going to introduce here is called cross-region topology. Here, pairs of brokers are separated regionally. Producers and consumers can be regionally separated, and messages are available at the local broker. So if a consumer is consuming a message and the message is already in the broker, the localized latency, it can be lower here. Obviously, the end-to-end latency will be impacted by the distance between the regions. Here, message durability for persistent messages is still available across AZs, but not across regions unless you actually replicate those queues. Finally, let's kind of deep dive one of these configuration files. So here, I'm looking at the configuration of a relatively complex network, the active standby mesh that we see in the top right. This is the configuration of broker one. And if you look here, you'll notice there's actually 4 lines here. 2 network connectors are defined for each of the connections from broker 1 to broker 2 and broker 1 to broker 3. And here we actually use 2 separate connectors for topics and queues. And what I can do is let's zoom in here on the queue connector here from broker 1 to broker 2. Remember that conduit subscription setting that allows messages to pass through between brokers without duplication? Here we have it set to false, so each subscription will get its own message, and we can load balance across all the consumers that connect to broker 2 in this case. The excluded destination sub-element is used here with the greater than filter, which means it excludes all topics from this connector. So only queues will be able to use this connector where duplicated messages are used for subscription. Also notice that consumer TTL is set to 1 to ensure only one hop. Message TTL is set to -1, which means it's unlimited and it can continue to hop until the message gets to its destination. The final couple of things to look at, this also uses that master slave URI prefix that I described, where each of the active and standby brokers, in this case -1 and -2, are used, and the connector will identify the correct active broker and only establish a connection to one broker at a time. If we deep dive the topic configuration as well, we'd see something similar, obviously with excluding queues instead of topics. So that was an introduction to Amazon MQ and network of brokers. Hopefully that gave you a good idea of what it's about. Now I'm going to hand off to Sandeep to talk about his use case. Sandeep has been a user of Amazon MQ from the very beginning. He was one of our early beta customers for the network of brokers feature. He has a great and interesting story. So thank you very much.
Thank you, Astaji, for such a nice introduction of enterprise messaging, Amazon MQ, and various Amazon MQ networks of broker topologies. I would also like to extend my thanks to our AWS STEM teams for their great support throughout our journey of migrating applications to Amazon MQ. This is Sandeep Dumad. I am an enterprise architect at S&P Global Ratings. For those who don't know about an S&P Global Ratings, we are world's leading providers of credit ratings. Our ratings and insights supports growth, transparency, and in the capital market and help market participants and investors to make educated and confident decisions. S&P Global Ratings provide high-quality market intelligence in form of credit ratings, research, and thought leadership. As you know, we are financial industry, we are a regulated industry. Some of our regulations mandate our applications and services to be highly available with very high SLA requirements. So today, what I'm going to talk to you is about our cloud migration journey. And in our cloud migration journey, how we use different messaging offerings that AWS has for migrating our applications off of our data centers to the AWS. And while doing that, what we have learned, what kind of architectural patterns that we have implemented, how we manage our high availability requirements using those offerings, those are the things that I'm going to talk to you about. But before we start with that, I would like to talk to you about our cloud migration journey. So it's always very easy to build a greenfield applications on cloud from scratch. But when you are given a task of migrating an enterprise applications from your on-prem data centers to the cloud, it brings whole sets of different kind of challenges. So one of the challenge that you would face is that um, typically in an enterprise, the you get an integrated ecosystem. Your application is connected with so many different subsystems and so many different shared services, and some of these connectivities are tight, might be tightly coupled as well. So that's the one big challenge that you would face while you're migrating your applications to the cloud. The second set of challenges that you face is the your non-cloud friendly data access layers and application architecture. These are the two major challenges that kind of uh, uh, puts a lot of restrictions how you go about defining your plan on migrating your application from on-prem data centers to the cloud. There are other sets of challenges as well that you may face while migrating your applications to the cloud. So today, so let's take a little closer look at the integrated ecosystems. So as you see here in this diagram, there is an application. The application kind of interacts with multiple databases. Some databases are primary databases, some databases are linked databases. So a database can link to other database through a DB link. An application can interact with other application as an iframe. It can interact with a file system and then ETL jobs. It can also interacts with other systems or foundational services like service layer platforms or messaging platforms. And so here, as you see here, there are so many different dependencies that your application might be interacting with. When you are planning your cloud migration for this application, you have to make sure that you migrate your applications with all of its dependencies. Now, if we think about these dependencies, then it turns out to be that these dependencies are of two different classes. These dependencies are either direct dependencies or indirect dependencies. Like for example, here the primary database is a direct dependency and the linked database is an indirect dependency. As well as these dependencies could be a soft dependency or hard dependency. So for an example, the database is kind of a hard dependency, and the services or messaging player is the soft dependency. What do we mean by soft dependency? Is that the latency of that dependency may play a role on performance of an application, but it may not be as critical as compared to the latency of the hard dependency elements like database. If you keep a database like 100 miles away from your application, of course you're gonna get a major performance impact over JDBC compared to what you get on HTTP, because the nature the protocol operates. So the messaging is a direct but soft dependency. And because it's a direct and soft dependency, what we did was we planned to migrate our messaging platform beforehand before we start migrating our applications over to the cloud. And that kind of gives you a flexibility in terms of your workload classification and prioritization for migrating your applications to the cloud. Now, we decided to migrate our messaging platform to the cloud. Now the next question was, but what is that messaging platform going to be on the cloud? Would that be a legacy platform that we have on-prem? Are we going to go install and configure that legacy platform on the cloud? Or we gonna leverage any cloud managed services that AWS offer? Now everything has its own challenges. Like one example, if we decide to set up and configure our legacy platform on cloud, the number one, our legacy platform may or may not be cloud ready depending on the vendor you may choose or you may have. The setup and configuration might be a lengthy when you are doing a cloud migration with a very tight timeline like what we had. That could be a challenge. Then there might be additional support and licensing costs and there might be maintenance overhead as well. But the cloud offering is also, it's not a free lunch as well, right? I mean, there are multiple options out there on AWS, as Saji already talked about. There's an SQS, there's an MQ. What to choose and what to use. You may or may not require to refactor your application depending on what you choose, and the level of refactoring also depends on your choices of the cloud services that you choose. So what we did was, in order for us to make a decision, we looked at our key requirements that we have, and then we looked at our architectural guiding principles. And then, our key requirements were the platform that we choose should be highly available. It should have at least 4 nines of availability. It should have a JMS support, because we have heavy investment on JMS as our messaging platforms protocol or specification, because we always believe in specification or de facto standards over proprietary protocol products and technologies. So we have very heavy investment on JMS. So the messaging broker that we choose should be JMS compliant. Of course, we have multi-cloud strategy as with any other enterprise. So whatever platform that we choose should be cloud portable. And because we had very short timeline, we wanted to make sure that our application migration from our legacy messaging platform to the cloud offering should be as quicker as possible, with very little changes in the code. So these were our high-level requirements. Our architectural guiding principles are specification and de facto standards or proprietary products and technology. We also wanted to make sure that there is no vendor lock-in, and we prefer managed services over engineered services, because we understand that engineering a service on cloud would be challenging because of the nature of the cloud resources. When you build anything on cloud, you have to make sure that you build for resiliency. Because any infrastructure component on cloud can go wrong due to various different factors. So you have to consider resilience in your mind when you are building a platform on the cloud. So we decide that the managed services, if we get and if it matches to all our requirement, I think is preferable over engineering a service or platform on the cloud. By looking at these requirements and enterprise guiding principles, we decided to go with the AWS provided cloud offerings. And then now the next set of questions that we had was, AWS provides so many different offerings. So how should we go about, how we went about using those offerings for our cloud migration? So as you see here in this, when we started in late 2017, we started off with SQS, because back then this was the only choice that you had got. And then in 2008, uh, late 2017, during reInvent, AWS announced Amazon MQ, and we quickly rushed and started leveraging Amazon MQ for the next set of pilot applications. And then in our cloud migration journey, and as well as the messaging platform migration journey, uh, we then migrated all our applications on Amazon MQ right now. And now we closely work with AWS, because high availability was the key requirement. And then we requested them to enable the networks of broker feature. And as soon as AWS made the Amazon's IMQ's networks of broker feature as GA. We worked with them, and then now we are working on moving our application workloads on Amazon IMQ networks of broker feature. So let's take a look at this journey a little bit more closely. So let's start off with our first leg of journey with SQS, as you see here in this diagram. So the SQS implementation is pretty straightforward. If you are building anything on cloud as a cloud native implementation, and then if you want to have any messaging requirement, then SQS is perfect candidate. What you do is you just create an SQS queue. To me, it's like I think it as a serverless messaging platform. SQS is like fully managed service, and it has built-in high availability. So you just go for it. But for the applications that we got, because we had all GMS applications or GMS messaging applications, what we did was, we use a GMS adapter on top of a SQS SDK. So our applications are not changed. They are still posting message as a GMS message, and those GMS message, as you see in this diagram, being consumed by SQS SDK and got converted into an SQS message, and then they are placed on SQS. And they are sitting on non-JMS compliant SQS queue, and then they are delivered to the consumer app, and then they do translation other way around. So this is a perfect solution for building cloud native applications. But there are some challenges with the SQS, right? The number one is that it has got limited GMS support. Now, GMS specification 1.0 or 2.0 has so many different capabilities which are defined as part of specification. The GMS adapter that we talked about does not support all of these capabilities. Like one example, number one thing was SQS queue are not FIFO by default. The first in, first out is the very basic principle for any GMS queue, and the applications kind of assume about that. So that is something that you need. The GMS, sorry, SQS has an at least once delivery model. What does that mean is, it can deliver a message for more than one time. And typically in GMS, for the queues, a message is delivered only once. And the SQS queue with the GMS adapter, they do not support exit transaction. So these are the limitations that we face, and that caused our applications to be re-architected. And that kind of caused a lot of time investment for those applications to be refactored. Uh, Now, the other challenge that we had was how to test out SQS from a local environment. Like if I got my machine, my desktop, and I want to test it out from my desktop, the options that I got is that I need to use access keys and secret key. Now, if you had got hundreds of developers in your team, like distributing hundreds of access key and secret key to those developers is basically nothing. It kind of increases your security risk. And you don't want to hand over these keys to so many people. Yes, you could always limit the scope of what they can do with those keys on AWS, but it's still a lot of maintenance overhead because you have to deal with now rotations and expirations and stuff like that. So by looking at these things, and then try to map them out to our requirements and guiding principles, the SQS falls short on cloud portability requirements, the easier application migration requirement, the specification and de facto standards, guiding principles, and the vendor lock-in. So with that, we in our second leg of journey, we migrated our applications to an Amazon MQ. As you see here, Amazon MQ is a managed active MQ service. It has got built-in high availability, and it has got full supports of JMS. And these are the three key things which we were looking for, and it was a perfect solutions for us when they introduced the Amazon MQ. Now, the kind of architecture that we use for leveraging an Amazon MQ is that we had to use an active MQ jar as part of our application, and like producer and consumer application, and they interact with Amazon MQ using the master slave architectural pattern. So the key thing to notice here is that the queues are GMS destination, like fully compliant GMS destination, and the message producer and consumer applications, they are using active MQ jar. They are not using Amazon MQ jar, and that's key for the cloud portability as well, right? Because at any point in time, if you want to build an application on some other cloud, which could be a cloud provided by other vendors, or on your data center, your applications and your consumer producer applications and their logic is not changed. So that's one of the key things. But it also got its own challenges. Like one example, the active Amazon MQ has a high availability built into its architecture, but it's not enough. We were looking for like at least 4 nines of SLA. The Amazon MQ out of the box kind of supports 3 nines of SLA because it's the primary standby mode. And then it also lacks the support of cross-region DR. Like most of the companies nowadays, they have cross-region DR set up for better, protection against region failures scenario. So Amazon MQ out of the box does not support with the default configuration the cross-region DR setup. So as you see here, by looking at Amazon MQ with and mapping it out to the requirements and guiding principles, Amazon MQ basically hits green on most of our requirements and guiding principles, except on high availability. It's kind of an amber because of that limited high availability that we get out of the box. Let's take a look at some scenarios. Let's take a closer look at what do we mean by high availability offering of Amazon MQ. So let's start with the first scenario, where let's make believe that the primary broker in this setup fails. So if that happens, the network connectivity between the message producer app and the primary broker, as well as between the consumer app and the primary broker, is broken. And the wire protocol that ActiveMQ uses between the application as well as the broker immediately identifies that the connectivity is broken, and it switches over to the standby broker. And basically, you don't need to make any change in your application configuration for that. It happens automatically. So this is the scenario. Now, the one important thing to note in this scenario is that all the messages that were posted on the primary broker, because those messages are stored in shared file system, are still accessible to the secondary broker. And you could just process your messages as like nothing happened. Let's take a look at the second scenario, the secondary broker failure. So you know what if your secondary broker goes down? This happens. It can happen uh, because of so many different reasons. In fact, this is how even Amazon does the patching on your broker. What they do is they do a patching on your secondary broker first, and then they would apply. If everything goes good, they will apply it to the primary broker, right? So if this scenario happens, the good thing about this architecture is that you don't need to worry about it, because your message producer and message consumer applications are still uh, connecting to the primary broker, even though the connectivity between the secondary broker and the your application is broken, doesn't matter to you. It just works fine. So this is the second scenario. Now let's take a look at the third high availability scenario. What if both broker fails? Like one example, primary broker goes down, the message producer and consumer application immediately learns about the event, and they try to switch over to the secondary broker. Unfortunately, now secondary broker goes down as well. Now in that case, you are kind of you lost both brokers, and message producer and consumer application now cannot do an inter application communication via messaging. And the only option which is left with you right at this moment is a manual switch over to your DR broker or DR region, depending on how you had configured your cloud architecture. Now if that happens, it might be a significant event when you have like so many applications, like hundreds of applications depend on messaging platform as a shared service. Because now every application has to manually maybe switch over to the DR site, and that might involve a lot of time and effort from various application teams. And even if you do that, the risk of you losing those in transit messages which are not processed yet, because these messages are not lost, they are still there in a primary site, but they are not available on DR site because they are not replicated across the region from your primary site to the DR site. So um, networks of broker is the perfect solution for solving that problem. Networks of broker, as Saji was talking about various topology, right? The one of the topology was uh, cross region mesh, right? You could do that, and if you do that, then your messages can automatically be replicated from your primary region to the secondary region, or maybe prod to DR, however you are configured. So that's the benefit of networks of broker. It gives you a better level of high availability, and it also it's an extension of ActiveMQ feature. It's like sorry, it's an extension of Amazon MQ, MQ default offering, and it's one of the active MQ feature. So this is what the architecture that we are implementing. As you see here, we got 3 brokers on our prod region. They are fully connected, so they are like kind of full mesh topology. And we also got the active standby broker on our DR region, and the active broker of this active standby topology is fully connected to the 3 brokers on the primary region or on the prod region. And you know what, this topology basically solves the problem that we just talked about. Number one, it gives you 3 brokers on the prod region. That means it enables you the 4 nines availability. And also in the case of the all brokers going down, it also takes care of replicating. If you had configured your replicated queue, then it also takes care of replicating your messages from primary region to the secondary region, and then made those messages available. So let's take a look at some of the high availability scenario with this configuration or this architecture that we are trying to implement. So the scenario number one is region failure. If there is some catastrophic event that happens and that knocks down your entire AWS primary region, and then what does that mean is all your brokers are down. If that happens, as you see here, your applications would automatically or manually, depending on your configuration, switch over to your DR region. And you know what? The As soon as you bring up your application, like producer and consumer application on DR region, they will start processing the messages, because those messages are still available uh, on the DR region, because those messages were replicated from primary region to DR region upon when the messages were posted in the primary region. So this architecture kind of takes care of that problem. Now let's take a look at the other high availability scenario. For example, your region is not going down, but what if your application has a DR event? What if the database which is linked to your application goes down? And this consumer application in this diagram has a DR event. Now you have to flip over the consumer application on DR side, but your message producer application is still in your prod region. Now if that happens, in the typical Amazon MQ configuration, probably you may have to switch over both producer as well as consumer applications over to the DR region, because your broker cannot extend across the region. But in this architecture, you don't have to worry about it. Your producer application can still stay in the prod region, and the consumer application can move over to the DR region, and your messages are still replicated across the region. And this is like kind of great solution for that. And what it helps is that this kind of scenarios, like individual application requiring the DR scenario, this kind of pretty common in enterprises when you have hundreds of applications. And if you get this kind of flexibility, it kind of helps you reduce your number of the time and effort that you need to put behind for handling those DR scenarios, because now you don't need to do a DR of cluster of applications from one region to other region. And what if it's manual? You could imagine that how much of effort you may have to put in place for doing that. So with that, Amazon MQ Network Stop Broker is a great solution as we looked at it from high availability point of view, and it kind of marks green in all our requirements and guiding principles. But it also comes with its own challenges. Number one challenge is it has got complex inner architecture. You got a lot more brokers to configure. That means some more maintenance compared to the normal Amazon MQ setup. And you know what, the setup and configuration could be a complex, because you have to have a lot of network links to be set up and then configured, managed, and stuff like that. But guess what, it's not that painful, because Amazon MQ is a managed service. Amazon does or AWS does a lot of heavy lifting for you. Now the second challenge is that application refactoring, right? So with an default Amazon MQ configuration, my broker list had only 2 brokers in master slave mode. Now if I have these 5 broker based topology with 4 brokers in mesh, my broker list for applications in prod region and DR region would be different. So there will be a configuration change, but it's a trivial configuration change, so you don't need to worry much about that. So with that, Amazon MQ networks of broker is kind of the great solution for matching to our need, providing us the kind of availability that we are looking for. With that, thank you so much. And if you have any question, please feel free to ask.
Thank you very much, Sandeep. I think Sandeep's use case is really how we envisioned Amazon MQ used by enterprises, and it's a great story. So just to close out in summary, Amazon MQ is a fully managed implementation that provides a fully JMS compliant broker that you can use to manage and migrate your existing applications without rewriting code, which again, I think Sandeep emphasized a lot. It does provide you with this multi-AZ durability, where messages are, or persistent messages anywhere, are stored across multiple AZs and thus never lost. And with the new network of brokers functionality, you get that higher availability that Sandeep's looking for, but also scalability. So the more brokers you add into that network, and if you manage them using the topologies we talked about, you can get significant scalability as well. So to close out, let me open up for some questions here. We have my contact information and Sandeep's contact information listed here. You can always connect with us if you need to. There are more Amazon MQ resources there listed at the bottom. If you follow that URL, you can learn a lot more about Amazon MQ. And with that, we'll open up for a few questions. Thank you very much.